In this video, we'll talk about using truth tables to test for properties of sentences and arguments in SL. In the last video, we worked out the complete truth table for this sentence. And we noted the result was 1 on all of the rows. Regardless of how the world actually is, whether z is 1 or 0, the sentence comes out 1. And that means that the long sentence is true, regardless of what's actually going on with z. In English, we had a name for a sentence like this. A tautology is a sentence that must be true, just as a matter of logic. In SL, truth tables give us a test for whether a sentence is a tautology or not. A sentence is a tautology in SL if it gets a value of 1 on every row of a complete truth table. You couldn't tell just by looking at it, but this sentence, z arrow z, biconditional z or not z, is a tautology, and the truth table allows us to show that. In the last video, we also did this truth table. It has a value of 1 on every row, so it gets a value of 1 regardless of the values of its parts. So this sentence is a tautology. And we did this truth table too, another tautology. What about this 16-line truth table that we saw at the end of the last video? It shows that the sentence is not a tautology because there's at least one row where it gets a value of 0. That is, this row down near the bottom. So this sentence is not a tautology. Recall that in English, we said that a contradiction is a sentence that must be false, just as a matter of logic. We can test whether a sentence of SL is a contradiction using a truth table. A sentence is a contradiction in SL if it gets a value of 0 on every row of a complete truth table. So P and not P is a contradiction. Recall that in English, a contingent sentence is one that is neither a tautology nor a contradiction. We can say something similar in SL. A contingent sentence of SL is one that is neither a tautology nor a contradiction of SL. We can show that a sentence isn't a tautology by finding one row where it gets a value of 0. And we can show that it's not a contradiction by finding one row where it gets a value of 1. So we can use truth tables to show contingency too. A sentence is contingent in SL if, on a complete truth table, it gets a value of 1 on at least one row and a value of 0 on at least one row. So, looking back at that 16-line truth table, just 2 of the lines is enough to show that the sentence is contingent. I could have chosen a different row where it gets a value of 1. I've highlighted one from near the top of the table. The point, though, is that these 2 rows are enough to show that the sentence is contingent. This sentence can get a value of 1 if the atomic sentences line up in the appropriate ways, and it can get a value of 0 if they line up differently. Now consider an argument. Here are 3 sentences. P arrow Q, P or R, Q. It's presented as an argument. The first 2 are premises. The final line is a conclusion. Recall that to say an argument is deductively valid means that it's impossible for the premises to be true and the conclusion false. To flip that around, we can say that an argument is invalid if it's possible for the premises to be true and the conclusion false. That gives us a test in SL. An argument is invalid in SL if there's at least one row of a complete truth table where the premises get a value of 1 and the conclusion gets a value of 0. To evaluate the argument, we put all the sentences together in the same truth table, and we look to see whether there's a row where the premises get 1 and the conclusion gets a 0. There is a row like that, here near the bottom. And since there is, the argument is invalid. To flip that around, an argument is valid in SL if there are no rows in a complete truth table where the premises get a value of 1 and the conclusion gets a 0. So consider this argument. Two premises and a conclusion. We have two sentence letters, so the complete truth table takes 4 rows. Having filled it out, we look to see if there are any rows where the premises get 1s and the conclusion gets a 0. That is, we look for a row where the results are 1, 1, 0. On the first row, the premises are 1s, but the conclusion is also 1. On the third row, the conclusion gets a 0, but so does the second premise. So there is no row where we get 1 for the premises and a 0 for the conclusion. And that means the argument's valid. This is a really significant result and a powerful tool, because the validity of this argument doesn't just jump off the screen. You aren't going to get to the point where you can just look at a string of symbols like this and have its validity appear around it like a kind of glow. What shows that it's valid is that we did a truth table, and in that truth table we considered all of the ways things could be, all the possible combinations of true and false for H and for J, and regardless of how those fit together, it couldn't be the case that the premises were true and the conclusion was false. So we've now developed a number of skills. We've developed the ability to construct truth tables for sentences of SL. We've seen how you can use truth tables to tell if a sentence is a tautology, a contradiction, or a contingent sentence. And we've seen how to use truth tables to tell if an argument is valid. You can also use truth tables to determine other properties. For example, to show that two sentences are logically equivalent, you show that they have the same truth value on every row of a complete truth table.